Hi, my name's Matt Green, and I want to thank Arvind, first off, for pretty much teeing off my entire talk and saving me about 20 slides. So I'm going to talk today on the other side, the constructive side. So we've already heard that Bitcoin may not be a particularly anonymous currency. The question is, what do we do about it? And I'm going to talk about some work that we have, a couple of pieces of work by some co-authors, which I will introduce a little later in the talk. Techniques called ZeroCoin and ZeroCash that allow us to anonymize the Bitcoin currency. So here's the quick summary of what Arvind just told us, is that Bitcoin, as far as we know, is not a particularly anonymous currency. We know that the transactions are recorded in a public ledger that everybody can download. Parties, right now, once you have this amazing public ledger, we don't do anything very sophisticated with it. We just essentially write checks from one identity to another. And as Arvind said, if people can identify, map your address to your identity, your real-world identity, you're in a very bad place. And I would say that, as Arvind said, if you're very paranoid, you may be able to prevent that from happening. But the truth is, most of us are not very paranoid and not particularly expert at this. So I think in the general case, you're not in a very good position with using Bitcoin for privacy. The other point I want to make is that this is something that should matter to all of us. Not because Bitcoin itself is necessarily the future. You may think that Bitcoin's a bit goofy, but the technology behind Bitcoin is a very important technology, and it's something that's very likely going to be with us for a long time. We should be looking at ways to improve it. The countermeasures we have are very weak, and they don't seem to address the problem even in the face of unsophisticated attacks. And the other thing that we should hope is that if we develop techniques to make Bitcoin private, we may even find applications for them that go beyond currency. So we can talk about that a little later. The outline of this talk, though, is I'm going to talk about two different approaches that we've taken that hopefully will give some direction to building new anonymous versions of Bitcoin. The first one is called ZeroCoin, and it's a technique that allows us to implement electronic cash in the Bitcoin protocol. The second one, which has not been published yet, is called ZeroCash. And the way we describe this is a way to make ZeroCoin practical and deployable and usable as a eCash currency. So I'm going to start with an introduction talking about ZeroCoin, because I think that helps to sort of tee up both of these. This is joint work, by the way, with my students Ian Myers and Christina Garman at Johns Hopkins, along with my colleague Avi Rubin. So when we started looking at Bitcoin, probably a couple of years ago, because we were sort of interested in privacy, the first thing we observed was that Bitcoin really doesn't give us very much privacy. And this was interesting because the academic community has spent a lot of time thinking about how to fix this problem for currency in general. In fact, if you go back to the 1980s or so, you'll find a whole line of works, beginning really with the work of David Chong, talking about how to build something called untraceable eCash. eCash, as most academic works do, kind of tried to tackle one problem without thinking about all of the practical issues that go with it. eCash sort of just assumed that we have a bank, a central bank that is willing to hand out anonymous currency to us. And then once we have that bank, well, there are a whole bunch of different ways we can use that bank to get coins. Those coins can be produced with blind signatures and so on. Well, the problem is that nobody in the history of academic eCash has ever managed to set up a working centralized bank. David Chong even founded a company to do this, and the company failed. In part because if you want to set up a bank, you have to get people to trust your currency first. It turns out that actually building a currency is a harder problem than making a private currency. But Bitcoin, fortunately, has solved that problem for us. The problem is we can't use existing eCash techniques with Bitcoin, because to do that, we would have to go introducing a centralized bank to a currency that is fundamentally decentralized. So what we need is a different technique. We need to get rid of this need for a centralized bank. And that brings us to ZeroCoin. The basic idea of ZeroCoin is that we're going to have a completely new approach to building eCash that gets rid of the need for the centralized bank. Now, the approach we use is actually related to a previous technique that was proposed by Tashma and Sander. The basic idea is that we take advantage of the fact that we have a decentralized public ledger, the blockchain, that's constructed by Bitcoin. And what we do is we use this to construct a decentralized laundry. It's a system that allows us to periodically wash our coins in a way that does not require us to trust one centralized party to help us. The great thing about this is the key ingredient of this technology, the blockchain, is already given to us by Bitcoin for free, so we really don't need to ask anything of the protocol. We just need to ensure that Bitcoin itself, in terms of building a bullet board, is a secure technology, and the rest of it is just crypto we can apply on top. So I'm going to try to give the high-level intuition of how ZeroCoin works, and I'm going to drill it a little deeper in just a second. So the basic idea of the original ZeroCoin protocol is that I have some Bitcoin. First of all, this is a layer that you're going to apply on top of the actual Bitcoin protocol. I have some Bitcoin. When I want to anonymize my Bitcoin, when I want to break that link between my current address and some future address that I'll spend with, I will take my Bitcoin and I will turn them into ZeroCoin, or ZeroCoins if you prefer. And what's going to happen in that process is they're going to get mixed up. All of the people on the network who are making these ZeroCoins are going to essentially shuffle their ZeroCoins together so that you won't be able to make a linkage between the creation of them and the later redemption of these ZeroCoins. At some future point, I can now redeem my ZeroCoins back into Bitcoin, preferably in a different and completely unrelated wallet. And this breaks all of this graph analysis stuff, because every time I vanish into that ZeroCoin network, there's essentially a break in that chain. There's no way to link the input address to the ultimate output address, and that should help you as long as you do this from time to time to reduce the amount of information you're leaking about your identity. So let's talk about how this could actually work. This is a very, very simple overview of what the ZeroCoin protocol looks like. So the first thing is that ZeroCoins are really just numbers. They're basically digital commitments to some large random serial number. If you don't know what a commitment is, probably you can just think of this as the encryption of a serial number. The important thing is that viewing that encryption or that commitment, you should not be able to tell what the serial number is. You can think of this as putting a number inside an envelope. Once you've minted these things, and by the way, they're very easy to make. Anybody can do this. They're not worth anything, since anyone can do them. Once you've actually created the ZeroCoin value, you need to put it onto the Bitcoin blockchain. And to do this, we introduce a new instruction in the Bitcoin system that allows you to go in and produce a transaction that spends, for example, 1 Bitcoin, in exchange for which you get to put this ZeroCoin value onto the blockchain for everybody to see. And the semantics of this transaction are such that anybody who sees this on the blockchain will know by verifying the inputs or correct Bitcoin that this is actually a valid ZeroCoin. It's now worth some money. At some later point, you can redeem that ZeroCoin back into Bitcoin. And to do this, this is where the complexity comes in. You first reveal that secret serial number you used to make the first ZeroCoin. You put that out, and you put that into a transaction. But secondly, you have to prove 2 things. You have to prove, first of all, that the serial number corresponds to a real ZeroCoin. And secondly, that that ZeroCoin is one of the set of ZeroCoins that was placed on the blockchain. One of the set of valid ZeroCoins for which somebody actually paid money. If you do that proof in a convincing way, you will be allowed by the protocol to transfer 1 Bitcoin into a wallet of your choice. And that's, at a high level, the entire protocol. The trick is in the way that we do that proof. We actually prove that this is a valid ZeroCoin, or this is the opening or spend of a valid ZeroCoin, using a zero-knowledge proof. Now, zero-knowledge proofs are a pretty old technology, but they're very, very powerful technology. The idea with zero-knowledge proofs is you can prove any statement, or most statements, very efficiently, but without revealing any additional information other than the fact that the statement is true. So here the statement that we're proving, again, is simply that there exists some ZeroCoin in the set of ZeroCoins that have been placed into the blockchain. And simultaneously, the serial number that we're revealing is the actual serial number inside of it. In other words, we know the opening of a commitment that causes that serial number to be revealed. Now, the great thing about this is since we have to prove that that serial number is what was inside the ZeroCoin that we actually put onto the blockchain, if the proof is valid, we will not be able to double spend. Because if we double spend, we're going to have to reveal that same serial number again. And that's trivially detectable. If anybody sees the serial number being used twice, they can reject that transaction. So we get a proof against double spending, provided that these zero-knowledge proofs work. Now the trick here is that we have to do this efficiently. And this is the only place where I'm going to get into a little bit of detail, but actually I'm going to just gloss over it at a high level. The approach that we use in ZeroCoin is actually to take advantage of another primitive called an accumulator. The one we use is based on strong RSA. So what we do is we collect all the zero coins on the blockchain into this accumulator. And then what we prove is really that the zero coin we are trying to spend is contained within this accumulator. The important thing here is that we can do that very efficiently. We have a proof of knowledge that's about 4 or 5 kilobytes for that proof. The problem is that we also need to prove that the serial number we're revealing is the one that's inside the zero coin. And that is not an efficient proof. In fact, the entire proof, the entire thing that we have to put on the blockchain adds up to about 25 kilobytes, and that's after we've optimized it. So after we had this initial result, we were very excited by it. By the way, this is, for crypto, this is great. I mean, 25 kilobytes is nothing. This is very efficient. So we went out to the Bitcoin community and we asked them what they thought about putting 25 kilobyte proofs onto the blockchain. And their answer was not really a great idea, and they were not particularly enthusiastic about putting this much kind of expansion onto the blockchain. We think there are some engineering solutions you could use to fix this, but really not something that is going to likely happen in the real Bitcoin currency. So the summary of ZeroCoin is we think it's a good first approach. It actually exists. It's a real piece of software. There's a library that we produced called libZeroCoin that you can download and play with. But the problem is the proofs are just too big. The coins also all have the same value. The idea is that you can transfer one Bitcoin into one ZeroCoin, and that denomination is fixed. Which means that if you want to spend actual fractional amounts of Bitcoin, you have to turn your ZeroCoins back into Bitcoins and then spend normally in Bitcoin worlds. So it's not really a full electronic currency, it's more like a washing layer. To address these problems, we have a new solution. This is called ZeroCash. The motivation behind this, or the history behind this, is that we presented these results in the Oakland conference in May. We also presented a short version of this at the Bitcoin conference, which also happened to be in San Jose in May. And it turns out that at both of those conferences, there were teams who are working on a new technology that allow you to make, it turns out, small zero-knowledge proofs. And these tools are called snarks. So right there at the conference where we're presenting this and saying we need a more efficient proof, a more efficient solution, we had some other cryptographers who really had that solution kind of ready for us. So snarks stand for Succinct Non-Interactive Arguments of Knowledge. It's a great crypto name. The particular snarks that we use were designed, in this case, they're part of a technology by Brian Parno and some other people at Microsoft Research. The basic idea of these proofs is that you can prove arbitrarily complex statements in a proof that is only 288 bytes. In other words, if you can express the statement you want to prove as an arithmetic circuit, which encompasses a lot of useful things, we can produce a tiny proof for almost anything. 288 bytes is not a big proof. This is much more Bitcoin transaction style. It's not a disaster. And the best news about this is that in addition to having these efficient proofs, there are actually C compilers that will take an arbitrary C program and produce a proof that the program was executed correctly on some secret unknown inputs. So in principle, all we should have to do at this point is we should simply take our code, our existing libZeroCoin code, and run it through a compiler and produce these very nice proofs. The problem is that the compilers that exist produce large circuits, and that leads to not very practical proofs. The proofs are very small, they're 288 bytes, but the time it takes to make one can run into the hours or even days. We really can't use that in a system like Bitcoin. So it turns out that there's a better way to do this. Now our co-authors, Eli Ben Sasson, Aaron Tromer, Medars Verza, and Alessandro Chiesa, have spent a lot of time optimizing these proofs. It turns out that the right way to do this is not to take the existing ZeroCoin construction, which uses RSA and some public key cryptographic techniques, but rather to throw all that stuff away and replace the techniques with components that are much easier to prove. The ones that we actually use are based on hash functions. So it turns out that we can build commitments from SHA-256. We can build accumulators using Merkle hash trees. And the amazing thing about these proofs is that we can actually prove statements about inputs and outputs of hash functions using relatively small circuits. For example, the implementation of SHA-2 that we use is about 30,000 gates. And that sounds like a lot, but it actually proves to be very efficient to prove even very complex statements using hash functions. So our new construction looks like this. We use, each coin is really the hash of some randomness and a serial number. That's the commitment. Once we have these coins, we place them together inside of a hash tree, which now serves as an accumulator. We place them at the very bottom at the leaves of the hash tree, and it's a 64-depth hash tree, which means we can store 2 to the 64 Zerocoins, which is more than I think you can possibly imagine people greed. And we can hash them up to a root. At any point we want to redeem, all we have to do is prove that we know the randomness, the R value, reveal the serial number, and prove that we know not only that R, but 64 hash values along the way up to the root of that tree. And that turns out to be very efficient using these snarks. So at some point we realized that we had a very efficient proof system, but we could do a lot of things with that we couldn't have done with the original Zerocoin. If these proofs are powerful and efficient, why do we need Bitcoin at all anymore? Why not take the entire Bitcoin transaction semantics and just throw it away? Put the entire system into Zerocoins, make everything anonymous, from the creation of coins, through the use of coins, spending of coins, allow you to split coins, merge coins, and do everything you ever want to do in a completely anonymous fashion. In other words, the only information that ever makes it into the blockchain is the fact that a transaction occurred. And it's actually very beautiful. We can do this with the snarks. Essentially, when we split a coin, all we have to do is show that we're creating 2 new coins, where the value of those 2 new coins totals to the original value of the coin that we're splitting. In other words, we reveal the serial number of the first coin, and we mint 2 new coins, and we issue a proof that just says the value of the 2 new coins is the same as the original. When we merge coins, which is the opposite side, we spend 2 coins, and then we prove that we've made a new coin that totals to the value of the 2 merged coins. We can even do transfers in a fully anonymous way. I can send money to you, such that nobody observing the blockchain knows who you are or how much I gave you. And to do this, I simply give you the secrets that are inside of the coin. I can encrypt them to your public key. I can even place that on the blockchain. And additionally, I embed an address. And the address is really the hash of some secret A, where you know, or sorry, some secret X, where you know X. Now the proof is, you can redeem that coin later by simply proving that you know that secret X. In other words, it's a one-way transfer. I give you the secrets along with embedding this hash of X, and since you know X, you are the only person who can later redeem that coin. So we can do all of the things you want to do with the currency, with one exception, which is transaction fees have to be public, but everything else can be anonymous. We have a name for this process. The generic transaction that we use is called a pour. The idea is that you can take in an arbitrary number of coins and output an arbitrary number of coins and even send them to other people. We call that pouring coins. Now the important question is this actually efficient? And here's the place where there is one little detail. You should always ask if there's a detail. There's one little detail I should mention. Before I get to that, I want to show you the proving times. So I mentioned before that the problem with Zerocoin 1 was that the proofs were huge. And it took a little bit of time to verify them. It took about a third of a second. Well, with these results, it's a little bit mixed. So in order to spend a coin or to merge a coin, when you want to actually make one of these proofs, it's not instantaneous. It takes about 87 seconds to 178 seconds. So that's a little bit of work. This is on a single core processor, by the way. But on the bright side, Bitcoin already takes about 10 minutes to confirm a transaction, maybe up to an hour. So adding 2 or 3 minutes to the spending time is not that much of a problem, and we think it will be optimized in the future. The proofs are tiny, they're 288 bytes. Verification time is extremely small, milliseconds. So really comparable to Bitcoin today. The important thing is all of the hard work happens inside the network. All of the fast stuff, the verification, happens inside the network, and the small proofs are there. So we're not going to drag the Bitcoin network down. And now I want to come to the one catch. There's one last thing that I want to address before I finish up here. The question is, should we do this? Should we even be doing this research? There's been a lot of people who have been criticizing us because we want to build anonymous currencies. I just want to add quickly that I think this is important research, not because we want to make it easier for people to commit crimes. The total size of these anonymous currencies is tiny. They're not going to make an appreciable difference in the amount of crime that occurs. But we think it's important because right now when you spend money, your transactions are hidden from your neighbors. But with Bitcoin, as I think Arvind pointed out, it's very possible that if you spend money, for example, visiting a doctor or going to a psychiatrist, that transaction will wind up being public to everybody you know. And we think that this kind of technology, no matter how we deploy it, is important. It's a next step that we should take. And so we're hoping to get this technology out there, and we're going to see what people do with it. So that's it. Thank you very much.
We have time for a few questions. Anybody?
Hi, so it's more of a comment. So I think we both, I think you're aware of some similar work that we're doing, and I think my main point is that actually that doesn't matter. So I think this work is too important to kind of just compete. I think I think it's great.
I'm sorry. So in the paper, which we're going to be releasing this week, we are actually there is another work independent at Microsoft Research that's doing some of this as well, and we do cite that. I'm sorry, I'm rushing through the slides, so I did want to give Markov credit because it's really nice work, and we are hoping that there's some good competition and that a good approach will emerge from this.
I think it's on. So I think also to give you credit, our work is work preliminaries. It was also a workshop, so I think there's plenty of work to do. And we have some, take it offline, let's do that.
Have you thought about how these proofs interact with scripts in Bitcoin?
So right now, Bitcoin has a really powerful scripting language that in theory, when it's activated, lets you do all kinds of things. These proofs right now, we only support a limited number of statements, like joining coins, spending coins, merging coins, and so on. In theory, you could build script, some version of script, into these proofs. So I can actually execute arbitrary programs and then prove them to be secure, or prove them to be valid. We don't support that. It would probably be very expensive to put that kind of thing into the code, but it is possible.
With the secure hash root thing that you're doing, is it necessary to have a single universal trusted party to decide on what those roots are, or can that be done distributed peer-to-peer as well?
It can be done distributed. So the network can help out computing that hash tree, but any party who has the blockchain can do it as well.
Can you say anything about minting transactions?
Sure. So minting transactions is actually very efficient. All you have to do is pick a serial number and a random number, and then hash them together to produce a coin. And then you put that coin into a special transaction, a mint transaction that you send to the network. There's no need for zero-knowledge proofs at all. You put that together and you send it in along with your payment of, or whatever it is that you're putting as an input. And then that produces the resulting coin. So it could be a coin-based transaction, for example.
I think this is very exciting and could have a lot of impact on the real world. And my question is the part about the public parameters that when they're generated, the people who generate them could embed a backdoor. Is it the case that we would have to rely on any one of the participants in that to honestly generate parameters without a backdoor?
So I want to clarify one thing I should have covered a little better. Any trapdoor that exists, let's say in the worst case somebody does retain that trapdoor, it would not allow you to de-anonymize transactions. The worst case is it would allow somebody else to basically make fake coins, counterfeit coins. So your privacy would be protected no matter what, which is a big deal. But the answer is that it is possible to build a system where multiple people collaborate to build those parameters, such that as long as any one of them is honest or a quorum is honest, you would have secure parameters. We don't have that built yet, but it's something we're considering. To make these proofs work, in order to spend coins, not verify them, but spend them, you need a large set of public parameters, and they total to about 1.2 gigabytes in size. Now, 1.2 gigabytes, if it were 1995, I think we'd all be freaking out. That's a lot. But it's 2013. That's about $1 worth of storage. So I don't think that's a deal breaker here. The best part is that if you're running a Bitcoin node, you already need to have about 16 gigabytes of data just to store the blockchain. So this represents about 7% of the total cost of the blockchain. So it's feasible. We hope for further improvements, but it's feasible. The other thing you should know is that somebody has to generate these parameters. Right now, that requires a trusted party, the same as ZeroCoin. Finding somebody to do that could be a bit of a challenge. We think that it's possible to find a dozen people on the internet who everybody trusts. We're hoping, anyway, because we want to do this. So, to sum up, we have a system that we think works, is efficient enough for deployment. But it's probably not going to wind up inside of the actual Bitcoin system. We want to release code. We're going to do that starting in May. So what do we do next if we want to get people to use this? I mean, this is real-world crypto. We want people to use the stuff that we're building. So what we're going to do with it next is we're going to release an alt-chain. We're going to release a client that implements all of the stuff I talked about here, allows these anonymous payments, and so on. And we're going to put it out there in an alternate currency. If you are tired of using Dogcoin, for example, you can use our ZeroCoin. It will give you anonymity.
But the question I have is, how are you going to generate those public parameters for your imminent real deployment?
Well, so we're going to come to Boulder and we're going to have you generate them because everybody trusts you. No, I don't know. I mean, the answer right now is that we're going to find a group of people who are interested in this, who are considered trustworthy. We're going to give them the code for generating it. We're going to ask them to review it. And we're going to go to Costco and buy a new computer. But maybe that answer is not sufficient for people. Maybe we need to do something a little bit more complex that uses multi-party calculation to do these kind of parameter generation things. Well, we're going to find out.
Thank you.
Any more questions? There's one more question.
Yeah.
Just one more. Does Zerocoin keep the there can only ever be this many Bitcoins property that Bitcoin has?
Yes. So right now we'll keep the same restrictions that exist on Bitcoin, which is that there are a fixed number of coins in the network. It would be trivially possible to change that. You could change that in Bitcoin as well, but fundamentally there's no technical difference here.
Okay, thanks.
Thank you. So you mentioned the trusted third party for the ZeroCash system. Do you need them to be honest all the time, or just one person being honest at one time and destroying the input parameters he had then?
Yeah, no, that's a great question. One person being honest at one time. Take the computer they used, set it on fire, and you never have to think about this again. It's not an online party who has to be trusted continuously.
I hope that we live in a world where one person can be honest one time.
I hope so. Unless it's the NSA.
Okay, let's thank the speaker again. Thank you. And we're ready to welcome our next speaker, Yifu Guo.